it just works, then why change it? But we are making good progress. We want to think on the Java side, introducing new features and making it just generally better, and we'll see some of that later. In 2017, we released JDK 9, and that's when we also introduced a whole new release model. Before that, we had releases every 2, 3, or even 4 years or so, and they were pretty major. When we moved to this new release model, we instead moved to a time-based model where we do 2 releases a year. So that's why you're seeing release numbers grow so quickly. But we'll see later as well, the releases are obviously smaller instead in size and scope. In 2021, we released JDK 17, which is an LTS release, long-term support. And one of the things there we did was to change the license. I'll get back to that. And then just for which will be released in September. So that's being stabilized right now. OpenJDK is the project in which we work together as a community on the next version of Java. So it's not just the next version in the sense of 23 coming out. It's in September, obviously. It's like the next version of Java and the next and the next and the next. We're exploring new features and improving things in general. OpenJDK is a place where people can meet up. This is much like the Java term itself. OpenJDK is also used to signify so many different things. People, for example, often have a tendency to say, we as well, say, run OpenJDK, right? And that's actually a misnomer in so many ways. First of all, OpenJDK doesn't actually produce binaries. It's a source code only project. The binaries you get from somebody who built them. That could be a vendor, it could be a private person, it could be, you could build it yourself, right? It's all open source, it's being developed in the open, you can observe all the development, it's discussed on mailing lists, we have our code on GitHub, all of that is open, but we do not produce binaries. It's a sort of a gentleman's agreement to level the playing field and make sure that everybody has equal opportunity to compete in the Java space, I guess. Our community is, and I'm going to show you on the next slide as well, it's a very big community, thriving and growing, I'm happy to say. So we have more and more contributors joining. We are hosting a lot of different projects. So the most notable project is obviously the JDK itself. That may be what people associate with OpenJDK, obviously. But there are other projects there as well. There are both projects to explore new features that will, if they succeed, eventually be integrated into the mainline JDK. But there are also other projects in support of that effort. So we have one project called Code Tools, for example, where among other things, there's a test framework. Testing the JDK turns out to be an interesting challenge because of its platform dependence. We need to run on all the different operating systems and architectures. It's both testing Java code and native code because the JVM is native, and so on and so forth. So there's a lot of tooling that we need that we wish we could use upstream or different dependencies or open source projects, but realistically, sort of, we need to develop our own things. And as I mentioned, all of that is on GitHub, so you can observe it. Our group is called that in GitHub as well. It's called OpenJDK. So github.com/OpenJDK. OpenJDK is a project. It has a governance model. You can read up on it more on openjdk.org. Not going to go into the details there, but there's a governing board that oversees the development and ensures that the community is thriving. And we have some bylaws to make sure that everything is sort of handled in the best possible way as a project, I guess. I did mention that the community is big and thriving and growing. This is depicting sort of the contributions. The big red thing here is Oracle Reddish, I guess. These are, by the way, issues fixed between JDK 11 and 22 per organization. And Oracle again in red. So as you can see, we're still the ones who contribute the most, at least when you look at the number of issues fixed. But it's true for a lot of different other measures as well. But there are significant contributions from lots of other organizations as well. One of the most interesting things here is actually, I'm going to argue, the blue one, which says independent. So those are people who have stepped up and contributed that are not directly tied to a company or an organization in the background. This is much bigger than it was a few years ago, and part of the reason is because we've made it so much easier, frankly, to both build, test, contribute to the JDK. I'm happy to say now that we are using Git and we're on GitHub and we're using PRs and all of that good stuff, right? That is like, I'm sure most other people feel is, how else would you do it? But that wasn't the case 5 years ago. We were using Mercurial and everything was handled very manually, and it was frankly just really hard to contribute. We changed all of that. There's a lot of, frankly, pretty awesome tooling that we built to interact with, making sure that even if the development logically happens in PRs, it's mirrored on mailing lists, so you can still observe it that way, and bug databases are updated automatically, things like that. And all of that has sort of made it easier, lowered the bar to make your first contribution. So if you are interested in contributing, please have a look. There's a getting started guide that you can have a look at, and we're welcoming your contributions. So I did mention that we shook up our release model pretty significantly a few years ago, and I think I mentioned most of this already. So we used to have feature-driven releases. That's how you did software development back in the days, I guess. The challenge with it is, of course, that it's very hard, especially if you're like defining new features in a platform like Java, right? Chances are that the design itself is very much unknown. It takes time to explore and figure out what to do, and then to implement that, and then to harden it on top of it. And since features were they were feature driven by that big, majorly complex thing, chances are that that feature made it in last. And let's just say that meant that we spent a lot of time trying to proactively prepare for and figure out what the world would look like 3 years from now. And that's like a recipe for disaster in our industry, I'm going to say. So we're very happy that we switched this model around. Now we do time-bound model, a time-bound model with 2 releases per year. Features are being developed on the side, but they go in when they're ready. And that means that we can take the time to explore and do them right, and still ship the other features right. Because one of the problems with the feature-driven release is that we did other good stuff as well. Some features went in the first year, but they still had to wait 3 years for that big thing that was holding up the release. Now it's a steady stream of good features, good improvements over time. We Oracle, this is not an OpenJDK mandatory thing, right? But most other vendors do the same thing that we do. We Oracle pick one release every 2 years. So every 4th release, beginning that we do 2 a year, that we call long-term support. And that is, we're going to keep supporting it for longer. Otherwise, they just keep replacing each other when the 6 months come along, sort of. So 17 was an LTS, 21 was an LTS, and if the model holds up, which, chances are it will, but plans can change, 25 will be an LTS next year. Right, and the LTS releases, this is also sort of a change. Back in the day, when we did our releases 2 to 3 years, we tended to do a first release, which was major, but then followed up with additional minor features that also went into that same release. So the update releases contained actual features. And that meant that there was no way for a customer or user to remain on a stable version and only get stability and security fixes. There was always functionality coming in as well. So that's also been changed now, where while there are still features that we do add, for example, security features, new crypto algorithms or new ports, we try to keep the amount of new functionality and fixes to a minimum, sort of really focus on stability. And then if you want the latest features, run the later versions instead. So here's what that sort of looks like as a chart. You see JDK 8 and JDK 9 back in the days. That was before we introduced our new model. And this is listing the number of JEPs, that's JDK enhancement proposals. They're sort of the key significant features that drive a lot of the roadmap of Java, I guess, and that we cover more in depth when it comes to documentation and, frankly, sort of marketing. And as you can see in JDK 8 and 9, there were a lot of JEPs. So we did many features, but obviously those releases were much longer as well. Then with the new release model, you can see that it's much more flat, right? Any release in itself, it may not be that significant and impressive, but together over time, we still add up to the sort of same delivery rate, if that makes sense. If you look very carefully, you'll also see that what I said about doing an LTS every 2 years is not actually true for the gap between 11 and 17. And that's because we at some point realized we started out with every 3 years. But then we realized at some point that a lot of the things that we were worried about, that the ecosystem wouldn't be able to pick up these releases as quickly, were not actually a problem. And as a matter of fact, we were worried that we wouldn't be able to do all of this because there's overhead in producing releases and supporting them and all of that. But as we noticed, right, every release is sort of similar to the previous one. And the ecosystem was frankly asking us to produce these LTSs more often. So we moved to a model where we do this every 2 years instead. So why is Oracle investing in Java? Well, the truth here is that Oracle is deeply dependent on Java. We use Java in a lot of our products, both open source and, hold your ears, or if you're allergic, proprietary products as well. We have several open source projects. I should probably have included a link here to our open source page. Oracle does much more open source than probably you think. There's a page we have, a web page where you can go to, oss.oracle.com, which covers many of the things that we do. Those things do include, obviously, Java itself, Helidon, which is a cloud-native microservices project, leveraging virtual threads, which is a feature we introduced in Java pretty recently. There's Tribu, not sure how to pronounce it, which is a machine learning library. There's sort of a long list of these. This is not an exhaustive list in any sense. Then there are proprietary products. Oracle has a Fusion stack. These are applications that are truly enormous. Think about the largest application you can think of, and then multiply that by some well-chosen factor. These are like fascinatingly large products, both in terms of lines of code and instances needed to run it and all that good stuff. So we have Fusion middleware and Fusion apps. They're Java-based. A large part of our cloud, OCI, or Oracle Cloud Infrastructure, is running Java for its services, the backend services. And Java even runs in the Oracle database, believe it or not. It's used for stored procedures, I think. But it's a very different sort of Java. So in either case, point being, it's important for Oracle to keep Java vibrant and moving forward. So the Java platform group at Oracle produces, we invest in obviously the code and new features. We do provide builds of the JDK. As I mentioned, there's no OpenJDK binary. It's always somebody who builds it, not the OpenJDK community in itself. We provide both OpenJDK builds of the OpenJDK, but we also, when that's the most recent feature release, it's available under the GPL v2 license, plus the class path exception, which is needed for linking on the Java level. It's sort of the standard license for Java-based things. We do have what we call the Oracle JDK. This used to be very different, but a few years ago, in 17, 18, in that time frame, we open sourced almost all our remaining features. The ones that remain in the Oracle JDK only are the ones that we couldn't, for various reasons, open source. License doesn't permit it, or it's functionality that is frankly going to die, sort of. It's not move forward functionality. Web Start, I believe, the thing that made it possible to run Java from your browser, but browsers don't support that anymore. That kind of thing, sort of. But effectively, Oracle JDK is the OpenJDK build with some additional small stuff in the background. And that's available under a license called the Oracle No-Fee Terms and Conditions, which makes it effectively, I'm not a lawyer, so please don't quote me on this or make business decisions of what I'm about to say, but basically allows you to run this for free in production and use it for whatever you want, more or less. And we make those builds available and support them. Support here, not meaning for pay. Like you can file bugs and we will look at them. you can't call us and necessarily get me on the line helping you, but we support those. We make them available to you for 3 years. So there's an overlap with the next LTS. There's always a 1 year overlap. So when 25 ships, we'll still have 21 available for 1 year. And after that, we move to a license called OTN, at which point you do need to pay us through the Java SE Universal subscription to get support for those. But this is sort of how we fund Java development at Oracle. It's important to Oracle. It's every product. This I think is true not just at Oracle, but in the world. Every product and project sort of needs to stand on its own to some extent. So this way we fund the Java development that makes it possible to do OpenJDK and get all of those features for free. The final thing I'll say about sort of the Oracle aspect of this is we have a huge investment in ARM and especially Ampere as part of our cloud. I'm not a cloud person. I work in the Java platform group, but let's just say that we like to think that we have a very price competitive offering when it comes to the ARM compute shapes. There's even a free tier available if you want to use that. That includes an ARM Ampere compute instance. So it's in our interest, Oracle Java platform group, to make sure that Java runs really, really well on Ampere and ARM. And that sort of segues us nicely into Java on ARM. So what did we have to do to make sure that it worked well? Well, the first thing to notice is, and I'm sure most of you are aware of this, is that Java uses this WARA model. So we tend to say we write platform-dependent code so that you don't have to. Java code in itself, the source code, is not platform-dependent. I mean, if you absolutely work on it, right, you can make it platform-dependent, but in effect, it's not. It compiles down to Java bytecode, which is still platform-independent. And you can do that ahead of time, months or even years, and Java is 30 years old almost. So one of my favorite small benchmarks that I picked up and ran back in 2000 still runs on the latest version of Java. And I guess maybe I have that on the next slide, but in either case, that's code that was written before ARM64 even existed, right? And it still just runs, right? So the platform independence is sort of a key strength of the Java platform. You can build it, you can write the code, you can compile it to Java bytecode, and you can still deploy it 30 years later on machines that did not exist at the time. So the JVM is where that magic happens. The JVM, as probably you all know, provides this abstraction layer, a virtual machine that, abstracts the hardware and the operating system and just sort of make things work. So porting Java or the JDK to a new platform is effectively porting the JVM. There are some other small things. We need to do minor adjustments in the class libraries. We need to do minor adjustments in the build system, but it's sort of the JVM where the work happens. Some history, and I will admit that I wasn't there at the time at Sun. I believe that Java was first ported to 32-bit ARM back in the Sun days. So I don't know, early 2000s maybe. You tell me. But at least that's sort of how it started. And then the ARM64 port got introduced in JDK 8 back in 2014. As I mentioned, on the core library side, there were effectively very small minor changes. But on the JVM side, this is sort of a deep dive technically. We do split normally the JVM up into 4 different areas. The first one is runtime, which is the rest. It's sort of weird to start with that, but it does a lot of different things. We group them all together. It's class loading, it's synchronization, threading, memory management to some extent, not the heap, but like allocating memory from the operating system, the low primitives for that. It also includes what we call the template interpreter, which is an interpreter that can run Java bytecode. So it can execute Java bytecode one instruction at a time. And that gets generated at startup, because even though we could do it ahead of time, there are benefits to doing that dynamically at startup. We can use CPU specific instruction and things like that, and sort of tailor make that interpreter so that it's fast. But that does mean that it is assembly, if you so will. It's not like it's generated assembly as well, but too many details. There are some other stubs in there as well. But that was one of the areas where we needed to spend some time. Garbage collection is more or less unaffected. There are things that we do want to leverage, I guess, as part of garbage collection, but most of it is all about memory accesses. And that's sort of the area between runtime and garbage collection. The memory model on ARM is slightly different than on x64, for example. Slightly weaker, slightly more relaxed, and therefore we needed to take that into account. So we had to redesign some of that. But more or less, the garbage collectors themselves were unaffected. We also have an area we call serviceability, which does a lot of monitoring and management and debugging aspects, that kind of thing. That area was, I'm going to say, pretty much unaffected, minor tweaks. The fourth area is where the vast majority of the work needed to happen, and that's in our JIT compilers. We can run Java using that bytecode interpreter, but it's very slow. And as a matter of fact, what makes Java go fast is the JIT compilers. So it's an optional component. It's not mandatory by the Java specification to have this. But for performance reasons, you want it. The JIT compilers will analyze what's being executed, and if it's executed enough, frequently enough, or often enough, then it will be optimized, really compiled. The bytecode will sort of be compiled down to native assembly code, if you so will. That obviously means a lot of architecture-specific stuff. Generating instructions, figuring out which optimizations that we need that we didn't already have that are especially useful maybe on ARM, ARM64. We also have something called intrinsics. These are, you can think of them as small accelerators. Maybe a good example is like string operations. Everything in Java turns out to be a string. Like literally everything. Like the only thing we do is move string characters back and forth in the end, for most things, obviously, right? There are exceptions. But that said, so things like index of, give me the offset of the first character or the first characters, the substring that looks like this. That kind of thing happens a lot. So we can try to have our JIT compilers do that, but in the end, it can be even more efficient to hand code that. And that's what we call an intrinsic. Array, copy, and clone are other examples of that. I don't know if we have like 100 different intrinsics, something like that. So porting them to ARM64 also makes a big difference. I'm not going to go through all of these in details. The point here being that when we design new features, when we have new projects like these are all OpenJDK projects that you can observe in the open. They have their own dedicated mailing lists and repositories and code changes. We make sure that whatever we come up with works on many different operating systems and many different architectures, even for the ones that don't exist yet, right? And that's obviously hard, but we try our best. I think one of the key examples of that maybe is on the Panama side. So Panama is a project where we are making it easier to interact with non-Java code or data. So data that is allocated on the native heap, not on the Java object heap, managed heap. Or for that sake, call out to native code, think C, C++ libraries. Why would we do that? Well, it turns out that people have spent man-decades or man-centuries or man-millennia working on super fast matrix multiplication loops, right? Or machine learning libraries, C, C++. Even for Python, most of the machine learning computation happens not in Python itself. Python is driving it, right? But the libraries that do it are all in C, C++ in the background. So in Panama, one of the things we do is a thing called the Vector API. This is an API, a Java level API that is looking to make it super simple to leverage SIMD instructions, single instruction, multiple data. So sort of act on many different cells, many different values within the same register, whatever you want to call it, in parallel. The Vector API that we are designing needs to be for Java for the long term and making sure that things work not just for what's there today, but for the future, needs to be CPU vector instruction or SIMD instruction agnostic. So we are making sure that it works both for Intel AVX and for Neon, or the ARM instructions at Neon, or SVE, for example, all of those sort of in parallel. So there's an abstraction layer that in the background then the JVM compiles down into the actual instruction set. So that's an example of something that we're keeping in mind, all of these different CPU architectures, and certainly ARM SVE as a special case of that when designing these kinds of things. For completeness, I'll mention that we're not expecting that a lot of people will use the vector API directly. Instead, we're expecting people to build libraries and things on top of it. So it's still a very low-level API, but it abstracts the concept of vectorized instructions. I think I'll leave it at that. The last one, Babylon here, started up last year, I guess we announced it, and it's sort of it's very early on, but that's super exciting. It's looking to really be able to write Java code and offload that onto both, like offload it, run it on CPUs, but also offload, if you call it that, I guess, on GPUs as well. Make it sort of abstract that whole concept, being able to execute the same general code on different different processing units in general. So stay tuned, but again, it's going to take some time to deliver. Okay, so now we're moving into the performance part of this, and I'll start by saying that performance, as always, varies. Only you know what you're running and in which environment you're running it in. So take my numbers on the next few slides with a grain of salt. But we like to think that they're sort of roughly at least representative for what people will see. As I mentioned earlier, we are delivering JDK releases on a six-month basis, and we make improvements in every release, right? In different areas, but on the whole, that means that, just by picking up the next version of Java, chances are that your thing will run faster. You don't necessarily have to leverage the new features, the new APIs we're doing, or anything like that. Just like pick up and run the latest version. No changes to your code. Maybe you compiled it 20 years ago, right? Just run it on a more recent version of Java, and you will likely get performance improvements. That's because many of them, not all, but many of them are in the JVM itself, or at least in the libraries on such a low level that it's not something you interact directly with, but rather just sort of hidden away, right? Just happens automatically. This slide, and I'll be clear here, is not running on ARM. It's running on a different CPU. I actually had the name here yesterday, but it felt like at this conference we're avoiding, or in this track at least, we're avoiding mentioning it. I think you can guess which one it is. I didn't have time to update the numbers. These are taken from a presentation, a keynote we had a couple of years ago. But ignoring the same general thing will be true on ARM as well. We are seeing continuous improvements. So you're seeing the JDK versions. Remember, the gap between 8 and 11 is slightly bigger than it looks in the chart here, right? 11 and 17 are closer than 8 and 11. But you can see a standard industry benchmark, and there are two different metrics. It's a throughput metric, and there's a pause time or latency metric as well. Both of them are improving continuously, right? So again, just by picking up newer versions of Java, you will likely see these kinds of improvements. So, however, though, looking at that specific same benchmark again, but running on Linux ARM, I just want to prove that there are improvements over time on ARM as well, right? So this is showing the throughput metric specifically, and I've normalized it over Java 8 or JDK 8. So it's 100% on 8, but over time you get improvements, right? So you will see that it goes up, not in every release, and there are reasons for that specific throughput measure not going up for this benchmark, right? But one of the key takeaways here is something I'll return to in a bit as well. The port was introduced around here. So that was the first version. We did not have a lot of, we shipped the version because it's better to have something in place than nothing at all. But then we spent time optimizing it, and that's sort of what you're seeing here. Over time, it gets better and better, and especially for a newly introduced port like Linux ARM64. I've cherry-picked another benchmark. This is from the Da Capo benchmark suite, which is another one we use to drive development. Here a lower score is better, and the same general pattern is true. Over time, performance improves. So how does that happen? Well, I alluded to it. This is probably familiar, right? You can try to just improve things randomly, but one of the best ways is run your thing, run your application, figure out what's going on, profile and find the opportunities, and try things out, try to improve things. In some cases, it doesn't help. In other cases, you'll find that good improvement. And you go through this. This is what I've done. This is what we've done the last 30 years of Java, and we continue doing. Some of the things you find are going to be surprising. I read an article series by, I'm going to butcher the pronunciation, I think his name is Michael Abrash, maybe. He has a graphics, what's it called? The graphics programming black book. It's awesome. You should read it. He goes through what it was like to optimize loops for like doing not just graphics programming, but in general, like optimizing code back in the 80s and 90s, and all the sort of subtle microarchitecture things that he had to think about. Fortunately, that's much, 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 much easier today, but there are still things where we're surprised, right? It's like, oh, you shouldn't have that instruction after this. That you can only find by analyzing things. And fortunately, this is where our collaboration with Ampere has been extremely valuable, because they have insights on the hardware level, right? Oh, we can see in the cache protocol that this and that is happening, and we know what that means when it comes to optimizing on the Java side. So very invaluable to our improvements in Java the last few years. There are some examples here. There are things we do in Java to speed up locking. Locking is effectively free in Java, which is pretty fascinating when it comes down to it. But that is because we have heuristics and pretty sophisticated locking implementation where we do tune for each individual CPU. So that was one of the things we did together with Ampere, tuning those things. We did find that we did instruction cache flushing redundantly, so did more of it than needed. And that turned out just to be slightly more costly on Ampere than other CPUs we had seen in the past. So it's like, yeah, we hadn't seen it, but now we profiled and we saw it and we fixed it, right? Similarly for memory barriers, the things that, the small things we inject to make sure that data is seen in the right order, we had redundant memory barriers as well. Those turned out to be more costly on ARM. So by removing them, we speed up performance. Things like that. Lots of subtle small things. I'll bring up a couple of sort of key improvements that we have done over the last 10 years. This one is from JDK 11. It's actually from 9, but we don't do 9 as an LTS. So the release you'll find it in today is 11. It's called compact strings. As I mentioned, everything in Java is a string, sort of. And it turns out that Java, from its design back in the 90s, is using 2-byte characters, so 16-bit characters. But as you might guess, a lot of strings are not using the top 8 bits, right? Lots of it is just like HTML or XML even, without those top bits set. So wouldn't it be nice if we could represent optimistically strings as 8-bit character arrays? And then if we got it wrong, we'll fall back to 16, the original implementation instead. So that's exactly what we did. It turns out that this has 2 key benefits. One is the obvious one, it's footprint. If everything more or less on the Java heap is a string, then, well, we're more or less cutting that in half, right? It's not exactly right because there's overhead per object and string and things like that, but more or less, right? In practice, it turns out it's more 5 to 25% footprint reduction, but memory is costly. It's costly to buy, it's costly to power, it's costly to cool. So for all those reasons, that's a significant benefit in itself. The other one is the sort of the indirect effect, which is the cache locality and performance. So by having less data that you need to hold in your cache, you'll fit more valuable actual data in there. And that turns out to also have a nice performance effect, so 5 to 20%-ish. Again, numbers will vary. It should be noted that this optimization is not a pure win, because there are still strings that use those top bits, but it turns out, again, that the vast majority, even when running in locales, even Swedish has weird characters, right? Even in those locales, a lot of the data is still 8-bit clean, if I call it that, because we're referencing Java class names and, again, HTML that doesn't have those weird characters in them. Yeah. Another one that I'd like to highlight is, because this is partially my baby, is called ZGC. The Z here is sort of taken from the same ZFS back in the Sun Oracle days. Meaning really large, sort of, and also again the last character in the English alphabet, but though not in the Swedish one. It's a garbage collector. It's a garbage collector that is written and implemented to be super scalable, up to terabytes of heap, like really big heaps. You don't have to run with terabyte-sized heaps, but you can, and it's still going to scale. It doesn't scale with the live data. It scales, it sort of doesn't scale with the live data, full stop. So pause times are super short. It's microseconds, or at least milliseconds. What we're saying is milliseconds, but it turns out in practice we can sort of do better than that. It's not hard guarantees, hard real time, but it's good enough, sort of. So in most cases, you'll find less than 1 millisecond. And we also designed it to be auto-tuning. Don't specify any arguments, it will just do its thing. So here you're seeing an Oracle service, Oracle Cloud service that deployed this, and I think you can spot exactly when. This is like the latency and pause times that they had before and after. Pretty impressive stuff. I don't have the quote here, but the guy basically pointed out that like the CGC thing is just magic, right? It solved all of their latency and pause times problem overnight. And again, just like deploying on that same version, like the next version of Java, and changing the command line argument to opt into CGC. No code changes, no nothing. It just happened, right? So pretty cool stuff. Okay, and now if you're allergic to proprietary products, please close your eyes and ears, I guess. I am bringing this up not because I want to sell it to you. I'm bringing it up because, again, lots of performance numbers are made up on the spot, or for that sake are not necessarily representative. What I'm about to show you next are actual like things that are running. This is stuff that we ran. These are actual numbers from real applications. So I hope you forgive me for mentioning the proprietary product that we call Enterprise Performance Pack. What is it? Well, what we did is we realized that all of this investment we had made between JDK 8 and 17 was awesome, especially on ARM. Right, we had made all of those improvements. The version in 8 was good, like it functional and stable and all that, but that didn't have all the performance improvements. So what if we could take those improvements and package them up in such a way in JDK 8 that it still just works, right? People can just take this new thing and run it, and without any code changes, you get the performance improvements. So that's exactly what we did. 7 years worth of improvements on Java, the JVM, I should say, specifically, and on ARM in particular. The compact strings that I mentioned are included in this, for example, as an optimization, and ZDC would be as well. So if my math and my query skills in our bug system are up to snuff, 5,000 enhancements or so and 9,000 fixes. So this is what Ampere presented at one of our keynotes a couple of years ago. Actual improvements on Apache Spark, Apache Cassandra, other benchmarks, but it's a generally very interesting improvement, right? And again, don't look at this primarily from that perspective, but it's just like the improvements you're getting by moving up from 8 to 17, or to 21 beyond that, or to 22 that we've shipped. This is the kind of improvement you get without any code changes. And it's actually what allowed us at Oracle to migrate from another CPU architecture, not naming any names, to ARM for our own products, for our Fusion apps, for example. We were not able to do that because the performance was not there compared to the other CPU architecture, but now we can. Again, the reason why we didn't just move up to later versions of Java is these applications are enormous, right? But theoretically, that's the other way to do it. Just my point here being, move up to a later version of Java. Chances are you like it, right? So in summary, ARM64 has now for some time been a first-class platform for Java workloads. It was introduced back in 2014. We have constantly been improving on it. We are actively maintaining it as an OpenJDK community, and at Oracle, it's very important to us that it works because we have a huge investment in the platform itself. This is a good example, I want to say, of Java's strengths. Java being platform independent and promising this, you write it once and you run it anywhere. this is literally an example of code that was written many, many years ago before ARM64 existed, and now it runs on ARM64 without you having to make any changes. That's pretty cool, frankly. And we are making improvements in every JDK release. We work very closely with Ampere. Thank you for working with us on finding and improving on Java continuously. And a lot of these changes and improvements, again, are on the JVM level, sort of. So again, pick up your greatest version of Java, and chances are you can just get them without changing anything. I will leave this slide open. It's a set of resources, everything from the OpenJDK project itself to the current release that we're working on, JDK 23. We have mailing lists where you can observe all the development that is happening transparently in the open. Our code is on GitHub. You can find releases, information about the various releases, going back in history and looking, projecting into the future on java.com/releases. There's dev.java, where you can find development resources. So if you're a Java developer and want to understand like how can I do this in Java, that's a good place to go. There's inside.java, where we cover, there's content produced from the Oracle team at Java. Sorry, the Java team at Oracle. Wow. Okay. And there's a page there as well for open positions in the Java platform group. We're hiring all the different areas, both JVM and management and performance team and infrastructure team. If you like makefiles and shell scripts, talk to us. And you can find our containers on the container registry there. And again, if you want to contribute to OpenJDK, please do. Please do. Even small things like picking up early access builds of our next release, JDK 23, of our project. We released an early access build of what we call Valhalla the other day. Value types, super exciting things. We've been working on that project the last 9 years, I think. And it's finally getting close to deliver. Try it out, file a bug, read the email lists. Yeah, let us know what you think. And with that, I think I'm out of time, but maybe a quick question or two. Yes. Yes. So I'm going to butcher. One of the challenges with doing a release every 6 months is that I never remember which release what went into, right? Because there are just too many of them. But let's say it is in 11. It's certainly in 17. If you and I should say there's a concept called generations in garbage collection. The generational support for ZGC, which is a key sort of feature of garbage collectors in the end, was only introduced recently. So if you want that, you want JDK 21 or later, but it's all in OpenJDK. Every feature I've talked about here, apart from the Enterprise Performance Pack product itself, is open source. But I should clarify, all the features in Enterprise Performance Pack as well are in OpenJDK, right? They're open source. It's just that the packaging of that is something that is proprietary. Yes.
Yeah, I have questions. First, I noticed in one of your earlier slides when it kind of had a visualization of the contributions to open source Java. There was one company that I noticed was missing from that list, and that was AMD.
Ah.
And I'm interested as to perhaps if you have a sort of an explanation as to why AMD isn't a huge contributor to open source Java, whereas in contrast, Intel, Amazon, Tencent, all are all.
Right. So AMD have been contributing in the past. This obviously varies a bit over time, and it could well be that AMD is in there somewhere, right? The boxes get kind of small. Maybe they're there. A lot of that is like it varies over time. As I said, we had very close collaboration with AMD 10 years ago, I guess. But again, it sort of varies over time. Still work very closely together with Intel as well. So a lot of that is obviously the same general functionality. But yeah, no, again, varies over time, I guess.
You didn't answer part of my question about the different open source projects that get integrated into Java Virtual Machine. You said specifically Valhalla is really close. I'm really curious about Panama and the improvements in the Cindy.
Yes.
Cindy performance.
Yes. So the projects. Okay, wrong. Whatever. There we are. Almost had it. I almost had it. There we go. So these are roughly in delivery order, but don't like take that as a guarantee or anything. So Lube has delivered, ZDC has delivered, Panama has delivered a lot or a significant part of it, and especially the part where you can more easily. It's always been possible, but it's been sort of clunky to have data off of the normal Java heap, or for that say call out to native libraries. So Panama is simplifying that a lot. That we call the foreign function and memory part of Panama. So that actually isn't the JDK since so recently. The vector API is still what we call incubating. Part of the reason for that is that it sort of depends on Valhalla. In order to get all of that to work really well, both footprint-wise and performance-wise, we need to be able to more densely pack the data. And that's effectively what Valhalla allows us to do. So instead of having, you can think of like you have a point in Java, right? An X and a Y coordinate in a class. If you have an array of points, you'd think that Java would do the performant thing and just have the XY, XY, XY in memory, densely packed. But that's not how it works, unfortunately. Everything is an object, so everything is an individual object on the heap, and the array is just an array of pointers to the actual objects. Valhalla promises to allow us to pack things more densely. And that's sort of exactly what vectors are in the end, right? So it's still incubating in waiting for Valhalla to deliver. And I'll just say for completeness, when I say that Valhalla is getting closer to deliver, like don't hold your breath. It's still not this fall, but you know, from a given that we've worked on it for almost a decade, so many insights were won the last year, and we're now very optimistic about like being very much closer to delivery.
On the performance side, could you hypothetically like get both projects, build your JVM, and then just performance test with those?
Fantastic question. So yes, they are technically different projects, but there is an effort. There's a repository somewhere. I'm not sure if it's on the. I think it's on the Panama side in the GitHub Panama repository. Sort of. There's a branch probably somewhere, which actually merges both. So it takes Valhalla and integrates the vector implementation as well. It's obviously not production ready, right? But that said, if you want to play around with it, I believe that there is a relatively up-to-date version of that as well. It is super exciting, frankly.
Oh yeah, so what languages are like competitors to Java now, and then what is the Java community doing to enhance Java to stay relevant after all these decades?
Yeah. So this is, I think, I saw you say FreeBSD is dying, right? And this has been our thing since back in the 90s as well. Java is always dying, and for some reason, I'm like, we're still happily working on it, and the community, as I said, is growing, right? And like, I didn't mention on the first slide, I believe I had, I think it's 6 million developers and it's 60 billion VMs running Java. That number is growing, right? Java is used a lot. That does mean that every language is a competitor. It just means like the question is just what are you using it for? What's your specific use case? And that's great. This competition, right? There are alternatives. If you have a special case where you want to use something else, awesome. What we try to have with Java is a good sort of home for anything. But there are limitations to anything. We're not trying to be the smallest runtime ever. We're not trying to be the most efficient necessarily language and runtime for machine learning in itself, right? We are providing the primitive so that others can build on top of it. And the ecosystem, I think, is where the true value is, the availability of all these libraries and people working on it. So everything is a competitor, and yet sort of Java tends to be a great place to just do your things. Does that sort of answer the question? Yeah.
That chart was great because if your second largest contributor beyond Oracle is Red Hat, they're an open source free software shop, followed by independents, followed by Amazon. You hesitate on, oh, this is proprietary. Are there any new projects that are going to be open or any old things on the shelves that might get opened up?
So as I mentioned, yeah, exactly. No, and I mean, this is a deliberate choice we made back in 2017 and 18 that we're not competing with each other on the Java side. We are competing with other languages and runtimes. So let's come together. Like, let's open source everything. ZDZ that I mentioned was originally a proprietary feature that got open sourced as part of that effort back in 2017. We have another feature called JDK Flight Recorder, which goes way back 20 something years, more than 20 years now. Proprietary feature that was also open sourced as part of that. There are very, I like, again, there is a set of stuff in the Oracle JDK that is there and not open source, but I think you'll find that none of it is of interest for like the future, right? It's like it's dying technology that we can't open source again for legal reasons or because it doesn't make sense anymore. So we do all of this in the open, transparently, and moving Java forward that way together. And yes, it's a good point that you point out. Red Hat is a fantastic partner to work with. They've been working on Java very seriously for 20 something years as well, 30 maybe. So it's a good community, great people.
I popped in a little bit late, but you might have, I don't, you may have answered this, but if you did, sorry, but these projects that are helping like for performance and speed up and everything on ARM, are these available to other languages that run on the JVM, or are these specifically Java?
That's a good question as well. So I think I'm right when I say that, again, most of the improvements are in the JVM itself. And that means that no matter what you run on top of the JVM, you will get them, right? So I can't speak for all the different languages that are running on top of the JVM, but many of them at least will benefit from the same optimizations we do in the JIT compiler or the ZDC garbage collector improvements, that sort of thing. Compact strings, I guess it depends on how your language represents strings, if it's using our string implementation in Java as a basis for that sort of or not. But a lot of it will be beneficial for anything running on the JVM. Final question? Then we're done. Thank you very much.